Welcome back. So today we are going to derive the one-dimensional heat equation. And it might sound like a pretty simple thing to do, but this is a big step to get practice at deriving partial differential equations to encode physics, basic physics that we know, like conservation of thermal energy. In a few lectures, I'll derive the 2D heat equation, and we'll get the heat equation and Laplace's equation for the steady state distribution. And this is the same kind of idea of how you derive the continuity equation, Navier-Stokes equation. Really how we encode physics in general is that we kind of keep track of all of the, some quantity like thermal energy, and we derive a conservation law-based PDE for that. So I'm going to jump right in. I'm super excited. This is one of my kind of favorites. OK, so we're going to consider the temperature distribution U of x and t in a thin metal rod. So let's actually draw like a little, you can just kind of imagine this as a wire or a little piece of metal that you can pick up at the hardware store. And U of x and t is the temperature distribution, literally the temperature at every point in x. So x is how far I am along this, this thin metal rod. U is the temperature distribution, and it's evolving in time. OK, so let's just draw x. And the boundary conditions are going to be 0 and L, x equals 0 and x equals L. And U of x and t is this temperature distribution that's changing in space and in time. And so what we're going to do is we're going to use common sense that there's like a conservation of thermal energy in this thin metal rod, and we're going to derive a partial differential equation that has to be true for that conservation to be satisfied. Now, I'm going to assume a couple of things here. I'm going to assume, for example, that this is an insulated rod. So we're going to put kind of a styrofoam sheath around it. And maybe I will fix the temperature at the boundary conditions or insulate the boundary conditions. And I'll start with some initial temperature distribution, U of x at time 0. So that would be my initial condition. And what we eventually want to do is, we're going to derive that partial differential equation. But then we want to solve that PDE for the distribution U of x and t everywhere in space at later times t. I want to know what the temperature distribution will be like in the future. And this is important for lots of applications, right? Predicting the thermal distribution in an object is a critical capability when we design engineering systems, like a space shuttle re-entering the Earth's atmosphere. We better be able to tell how the temperature distribution on the surface changes in space and in time. OK? Good. So let's jump in. We are, essentially going to, like I said, use common sense to derive this partial differential equation. So let's start doing this. And I want to write this out in words first. So the rate of change of heat energy in time, the rate of change of heat energy in time is going to equal the heat flux through the boundary at every point in space. If I take, this is actually going to be a really important thing. We're going to take a little segment of this, and we're going to zoom into that segment. We're going to zoom in to a little segment here. OK. If we zoom into that little segment, then there will be heat flux through the boundary into the next element. And if it's insulated, it won't go out to space, but it'll only go to its neighboring little elements to the left or to the right of it. So the rate of change of heat energy in this, this rod in time is going to equal, the only way it can change is if heat energy fluxes out through conduction to its neighbors. So heat flux through the boundary, to its neighbors, plus any heat generated at a point in space, plus any heat energy generated in kind of x and t, at any point in space or in time. And so, for example, maybe I have a fancy way of heating up a little local patch of this and putting in heat energy. Maybe I can inject heat energy with a blowtorch at this point and create, this kind of heat spike here. That would be adding heat energy like this. Or maybe my thin metal rod is not actually made of, copper or something like that. Maybe it's made of plutonium and it's actually generating, heat through some atomic process. Maybe there's some atomic process generating heat energy at each of these local segments. Now, the cool thing about this is that this is just a basic statement that if I insulate this object, the only way that the total heat energy, the total thermal energy of the system can change in time is through heat flux through the boundaries, or if I zoom into a little patch, through its neighbors, and if there is heat energy generated at each of these local pieces in time, either through external forcing or through molecular atomic processes like fission. And so this is just a very, very general statement of the conservation of thermal energy. This is basically always true. Even for exotic materials, this is going to be true. Even if my boundary was not insulated, then I could have heat energy lost through radiation. This would be, I would be able to include radiation effects in here as well. Thermal effects, nuclear effects, radiation effects. And it's true integrated over the entire domain, but it's also true when I zoom into a teeny tiny little local segment of the domain. And that's going to be a really important point. So now I'm going to write each of these three terms in math, okay? And maybe I will do this in pink here. So the total heat energy is given by our temperature, U of X and T, but the particular material, let's say this is copper or lead or whatever material this is, has some physical properties that tell me how much heat energy there is at a given temperature and at a given mass or density. So it's not just U of X and T. I have to multiply this by rho of X, the density, and by C of X, the specific heat. So I'm going to write these down, otherwise I'll forget. So this is the density. This is the specific heat, kind of the heat capacity of the object. And this whole thing here is the heat energy. The heat energy in some little kind of infinitesimal segment of this would be the heat energy in that little infinitesimal segment. You could multiply this by a delta x if you really want, okay? And what we're saying is that the time rate of change of this, the ddt of this quantity, ddt, really this is a partial derivative with respect to time, partial ddt of the heat energy there can only be a change in heat energy due to flux through the boundaries or source or sink terms, heat energy generated or lost at points in space. Good, okay. And so this is going to equal, so let's keep the color scheme here. This is going to equal heat flux through the boundary at each point. I'm going to write this as a minus partial Q partial X. I haven't told you what Q is. This is a heat flux quantity that is related to the temperature. I'm going to derive it over here, plus these sourcing terms Q of X and T. Okay? This is literally the only way that the heat energy can change in a little segment is by heat flux through the boundaries to its neighbors, or a source or sink term. Maybe this Q is radiating energy, or maybe there's an atomic process generating heat energy, or maybe you're hitting this point with a blowtorch. That all lives inside this forcing function Q. Okay, good. And I want to also label these. This is the heat flux through boundary, and this is my my kind of source term. And we call it a source, but it can also be a sink. You can also be bleeding energy off through radiation and things like that by emitting light. Okay, fantastic. So I want to tell you what this Q is. I haven't defined this Q yet, and it's really important. So I haven't told you why I have minus partial Q partial X as the heat flux. That's what I want to derive now. And then we'll go back and we'll simplify this into a nice PDE that we can work with using Fourier's law of heat conduction. Good. And I'll, of course, at the end, like I normally try to do, I will kind of zoom out and re-summarize all of these pieces. But again, remember, all we're trying to do is write down conservation of heat energy and figure out what could change the heat energy in time and in space. And now I'm zooming into the heat flux term, into this term here, because this is a little bit confusing. So let's say I have a little teeny segment of this, a little infinitesimal delta x segment. And so I have what I'm going to call this Q of x and t is called the heat flux. This is the heat flux from left to right. And I have to say from left to right because that convention of it going from left to right is what allows me to get this sign correct. So I have to actually pick that heat flux is defined. Positive heat flux goes from left to right. So this gains heat if heat fluxes in from the left, and it loses heat if it flows out to the right. Okay? Good. And so what I want to do, this has the units of thermal energy per time. Thermal energy per time. That's what this heat flux is. And I am going to derive, we will figure out what this Q is using Fourier's law of heat conduction. And maybe I'll tell you what it is. I don't want to like kind of beat around the bush. This is equal to some minus kappa partial u partial x. Okay, so I'll come back to this in a minute. So this is what it actually equals. And this is kind of intuitive. This fits our intuition that if I have two little segments next to each other, one that's very hot and one that's very cold, so that there is a gradient of the temperature in space. This is partial u partial x, meaning there is a change of temperature in the x direction. If I have that partial u partial x, then I expect there to be a large heat flux at that location. Okay, so the heat flux at a location x is directly proportional to the gradient of the temperature at that point x. So if I have a really steep temperature gradient, really, really hot on one side, really, really cold on the other, this is a big number, and I get a lot of heat flux. This is common sense, okay? But it was, this took a long time to be derived. This is a major result. So this Q of x and t, what I want to do is actually like write this down. So we have Q kind of coming in here. This is Q at x and t, Q of x and t. And there's also some little infinitesimal heat flux out. This is Q at x plus delta x and time. And so if these two are equal to each other, if the amount of heat flux in is equal to the heat flux out, then this term is 0. There's no rate of change of heat energy in this little volume. And so that kind of tells you why, now if there is a gradient in this heat flux, if I have more heat flux coming in than going out, then this should be a net positive rate of change of heat energy in this volume. If I have more heat flux leaving than entering, I should have a net rate of change decrease in the total heat energy in this volume. And so it's always a pain for me to get this sign right. But basically what we are computing is this partial Q partial x. The gradient of this Q heat flux tells me roughly if heat is on average entering or leaving this, this little infinitesimal volume. And so this is like the limit as delta x goes to 0 of Q of x and t minus Q of x plus delta x and t divided by delta x, and that's minus. So essentially what this says is that if I have more Q coming in than I have Q leaving, then I have this kind of, I always get the signs mixed up. Let me try to do this really, really carefully. What I'm trying to do is I'm trying to figure out why this is a minus sign and try to convince myself that this is actually correct. So let me just slow down a minute. If I have a negative gradient of Q. What that means is that Q is bigger coming in than going out. Q is bigger than medium than small. That is a negative gradient of Q. That is a negative partial Q partial X. And if I have a negative gradient of Q, that means I have more heat energy. This one's bigger than this one. I have more heat energy entering than leaving. So if I have a negative gradient of Q with respect to X, I have a positive rate of change of heat energy in that little volume. So when partial Q partial X is negative, this should be positive, and that's why I have that little negative sign out there. So this does fit with the convention that if I have a negative gradient of heat flux Q, that should have an increase in the heat energy in that little point X. Okay? Now, this Fourier law of heat conduction is really important. That's how right now what we have is a partial differential equation in terms of U and Q and little q. And what I want is to write this all as a little partial differential equation of U, the temperature. So I want to relate my heat flux directly to the temperature, and that's what the Fourier law of heat conduction allows us to do. So maybe I'll just give you a tiny little aside. This is where Fourier enters, and this is not for the last time. So Fourier has a treatise on heat conduction. It's a beautiful book. You can still read it today, translated, and it actually gives his thought process as he is deriving these equations and analyzing these equations. It's quite interesting. And actually, the heat equation is why Fourier developed the Fourier transform in the first place. So we'll see that later. And so Fourier made these three observations. He did experiments, or he collected the information from other people's experiments, Newton's experiments and others' experiments, that there is no heat flux when the temperature is constant. So if the temperature in this rod is constant from, at a point X, if it's the same temperature to the left and to the right, there will be no heat flux. That's the first observation. The second observation is that heat energy flows from high temperature to low temperatures. So if I have a high temperature on the left and a low temperature on the right, I will get a net flux of heat energy into this low temperature region. So heat flows from high temperature to low temperature. That's also observed. That's the second property. And the third property is that there is more heat flux when there is a larger temperature difference. If I butt up two little pieces of metal and they are 10 degrees different, that will conduct heat less fast than if there's 100 degrees difference. The bigger the temperature difference, the faster the heat flux. And so essentially, if you put all three of those together, you get Fourier's law of heat conduction, which is this expression here. The heat flux from left to right, the thermal energy flow in time, is equal to this minus kappa times partial U over partial X, the gradient of U with respect to space, the derivative of U in space. This kappa is really a kappa of X. Just like my specific heat and my density, I explicitly made these functions of X because I might have a weird material where it's copper here, and then it's lead, and then it's a mixture of copper and lead. These properties can change in space. Okay, good. And so this Fourier's law of heat conduction allows us now to write this PDE in the following way. Okay? And you'll notice that c and rho are not functions of time, so I can pull this partial derivative so it's hitting u. And so what I have is I have c of x times rho of x times partial u partial t equals, now partial q of partial x, the partial of q with respect to x, because q is partial u partial x, maybe I'll just write this out, negative ddx of negative kappa partial u partial x is just positive kappa partial squared u partial x squared. So this equals kappa partial squared u partial x squared, good, plus my source term. And I've dropped, u is a function of x and t, big Q is a function of x and t. I have actually, you'll notice here, I cheated for expediency's sake. I am assuming that this kappa is a constant. This this is the rate of thermal conduction, kind of how much heat is conducted, the conductivity. And I have assumed that that is a constant. Otherwise, when I take partial x, I'd actually have to do a chain rule, and I'd get a slightly more complicated expression here. And so I've kind of simplified my life. And if you simplify and basically say that C, rho, and kappa are constant in space, then you get this nice expression that partial u partial t equals kappa over c rho partial squared u partial x squared plus this constant, 1 over c rho times my forcing function. And that is essentially, I'm going to box this. I think we did it. This is the heat equation. This is the diffusion part of the heat equation. This is the diffusion constant. This is that positive constant alpha squared we talked about before that just tells me how heat is diffusing. And this is any forcing term. If I hit this thing with a blowtorch, if there are atomic fission processes causing heat energy to create, this is the forcing term here. And so this is pretty cool. This is the actual full-on heat equation for a constant material 1D thin metal rod. Okay, good. So in future lectures, what I'm going to do is I'm going to generalize this for 2D, 3D, ND. We're going to derive the n-dimensional heat equation for a three-dimensional object like the Earth or something like that. And it will be a partial differential equation where now this will be the Laplacian of u. Okay? Instead of just a second derivative with respect to x, it'll be the Laplacian of u. In fact, I'll just write down, we'll essentially get u sub t equals alpha squared Laplacian of u in the absence of forcing terms. So that's one thing we'll do. We will also look at how do you actually solve for the heat distribution given initial conditions and boundary conditions and source terms. We will solve for the steady state heat equation. So if in steady state this partial u partial t is 0, this partial u partial t is 0, and so in steady state we have the Laplacian of u equals 0, or if there's forcing, minus q. Okay, minus q, good. So that's all coming up to analyze these heat equations. But again, just re-summarizing. The way we derived this partial differential equation was by common sense. We know that in any material, in a one-dimensional metal rod of material, the total rate of change of heat energy and time has to come from two places. There can be heat flux through the boundaries, heat conduction, let's call this conduction through its boundaries to its neighbors, and then other forms of heat generation or loss, for example, through radiation or fission or a blowtorch or external heating or whatever. And this common sense conservation of heat energy allows us to mathematically write down this partial differential equation. Now we had to use things we knew, like this conservation of thermal energy. We assumed that was true. We also used all of the experiments that Fourier conglomerated into his law of heat conduction so that we could get this diffusion term here. But the process is actually relatively straightforward. You take a conservation law and some know-how and some vector calculus, and you derive a partial differential equation. All right, so more on this later soon. Thank you.